Right. Good morning, water worlders. So the first person that can yell out what season and where this image is, come see me and get some swag after the conference here. So any guesses? Where? Sacramento. Yeah, Sacramento. You got it back here in the corner. Perfect. That wasn't that hard, right? All right. So this is my first waterboard, so it's been really exciting to meet a lot of people and see what goes on here in Sacramento and learn about all the different efforts going around the state. And my talk is called Space Hydrology, Monitoring Water from Low Earth Orbit. We haven't actually discovered a ton of liquid water in orbit, but this is more focused on the ground. Just a disclaimer, I'm going to be as woke as I can be, but my presentation might be a little bit offensive to any flat earthers, so just letting you guys know. So my name's Orestis Herodotou. I'm a software engineer on the Planet Analytics team, and I work on automating machine learning models and at scale that work on our satellite imagery. I love sailing in the bay, and I'm also an anti-plastic pollution crusader, so shout out to the Datathon today. And I'm not a remote sensing expert, so go easy on me on some of the more technical aspects of some of this work I'm going to show. I've got lots to cover, so I'm going to try to breeze through some things, so feel free to ask me questions afterwards, and I'd be happy to go into depth. I'm going to do a little introduction on Planet. We used to be called Planet Labs, but now we're all grown up, so we dropped the labs. I'm going to cover some details on our imagery, talk about how our platform brings all of our processing together, and then look at some of the research impacts. And what I kind of want to show is that we're really entering a new era of remote sensing. It's sort of a golden era and a renaissance in the space sector. So I'm hoping to demonstrate that there's a lot of opportunity to use these remote sensing opportunities for environmental and economic challenges that face the state, and I hope that Planet Imagery can maybe contribute to solving a lot of these issues. So Planet is an integrated aerospace and data analytics company. We were founded in 2010 by some ex-NASA scientists from NASA Ames, and we're headquartered here in San Francisco. We've built the largest constellation of satellites in the history of mankind, and we've launched over 20 missions on all kinds of rockets from the Soyuz to the SpaceX. In 2017, we did a launch with 88 individual CubeSats like this one on an Indian rocket, and that got us to our goal of being able to image the entire Earth every day. So we cover the entire Earth's landmass roughly every day since 2017. So our motto is really, if you can't see it, you can't fix it. So we want to try to bring visibility and transparency to all the different dynamic changing parts of the Earth and be able to sort of aid in working to understand the impacts that humans are having on the planet, and then put that understanding towards addressing the UN Sustainable Development Goals. This is a picture of our 3 different types of satellites that we operate. The main satellite we're known for is called a Dove. We picked that name instead of the usual like eagle eye or hawk sort of bird of prey messaging that you usually see with satellites, and those make up what we call the PlanetScope constellation. We also have the Rapid Eye, which was a company that we acquired a few years back, and SkySat, which is our high-resolution sensor. And in addition to operating these satellites on orbit, we also have about 30 ground stations around the world. We have an automated mission control that takes care of communicating with the satellites, and we have automated publishing pipelines that handle enormous amounts of imagery that we download every day from space. So this is the DoveSat in a little bit more detail. It's what we call a 3U CubeSat format. It weighs about 4 kilograms, and this is what our daily imaging constellation is composed of. We have about 120 of these in orbit right now, and they've been consistently developed in a process that we call agile aerospace. So every 6 months or so, we're updating the configurations and improving the image quality and the different parts of the design, making them more effective. Each Dove is covered in art. I've actually gotten to draw and sign one of these, so I'm the first like Polish Cypriot guy that's gone to space basically from that. They're at an orbit of 475 kilometers, and this is an optical imaging sensor that covers a red, green, near IR wavelengths. This is a comparison between what a PlanetScope image typically looks like versus a Landsat 8 scene to give you kind of a sense of the scale of the resolution, which is about 3 to 5 meters per pixel. So the other two sensors are called SkySat and RapidEye. RapidEye includes a red edge band and has a really deep archive of imagery. The SkySat can do 1 meter resolution to sub-meter. We have about 14 of them in orbit. And the idea here is that with the monitoring constellation of PlanetScope, you're able to kind of detect course change around the world. And then if you see something interesting, you can task the SkySat satellite to get a really high definition view of that. We've also done video and stereo reconstruction for elevation with the SkySat, as well as like some really cool off-nadir shots that you can find on our website. So this is a comparison between SkySat and PlanetScope in San Francisco. So you can see, you guys can see that's a much sharper, this is at the same zoom level, but you can go in and get a lot more detail with SkySat. And neither of these sensors really are to the level where you're looking at people's watches or reading people's phones, so don't freak out. They're really meant for that overview to understand more widespread change. So our imagery products are generally published as what we call a cloud-optimized GeoTIFF. These are like your regular GeoTIFF files that are pretty standard in the industry for raster data. But they allow ranged HTTP reads, which means you can pull out just the data that you're looking for. So that might be just the bands or just a certain area of an image, which makes for really efficient workflows. And we publish a lot of different processing levels. For example, like a 16-bit analytic image for a scientific workflow where you need all 4 bands and you need to have a higher data quality. We also radiometrically correct images directly for you, so you can just kind of download a surface reflectance product from our website and skip having to do that work yourself if you feel like it. So our platform handles storing and publishing our imagery, and then we have a bunch of different APIs and tools, including graphical user interfaces for people to interact and download our imagery, as well as we serve web tiles. And you can also you can also access our imagery from third-party providers like QGIS or ArcGIS. And a lot of our customers will integrate directly with our APIs and create their own sort of value-added solutions. So they'll get like a notification that something new got published. They'll download that image straight into their workflow and then do whatever processing they want for their specific application. Some of the other solutions that we offer are our analytics platform, which is fairly new, but we're going into limited availability very soon this year. And that is our automated machine learning derived products. And so one example of that is an automated building and road land cover classification that we can do at whatever cadence, be it daily or monthly for larger areas. Our platform also allows you to kind of bundle and crop different imagery assets for just the areas you want. And like I said, get notifications on your specific area of interest. So you're not spending a ton of time like going through these millions of images trying to figure out which one you want. We also publish global base maps, which are mosaic composites. We have quarterly and monthly cloud-free time-lapse mosaics, and we also do custom mosaics. And they're also available with like OGC compliant web mapping services, so not much magic to get them into your web app or into your portal. This is one of my favorite parts of the talk, is talking about our open data projects. We are part of the Charter for Space and Major Disasters, which sounds really scary, but it's basically the foundation under which anytime there's a disaster, the UN asks us to contribute imagery for public consumption for volunteers and humanitarian organizations. So we have a whole section where we publish that imagery as fast as we can get it. And there's a team of people at Planet that basically is trying to stay up to date on, if there's a big hurricane that's going to come out, get ready and try to find the first cloud-free images of some areas. And you can see flooding or earthquake relief efforts be really affected by that, as well as, last year here in California, we published a lot of these images that dealt with the fires. We also have an education and research project, a program that is open to academics at universities, as well as students and other scientists. And that gives non-commercial download access up to 10,000 square kilometers of data per month. So it's a pretty nice free data plan. So if you're affiliated with a university or you're a student, I would love to see what you can come up with some of our free data, and you can just apply online to get this. So I'm going to switch into some of the hydrology highlights here. These are some use cases from around the world that show how planet imagery is being used in relation to asking both scientific and economic questions around water usage. And I think there's some really interesting stuff here that is definitely applicable to California. And one big theme that I want to keep in mind here, and I mentioned this sort of remote sensing revolution that's going on right now, is that we're finding that a lot of people are merging different data sets, bringing UAV and aerial imagery together with planet or ground measurements and other imagery from different satellites together. That's a really big theme here. And at the end, I'll talk a little bit about an effort to make that even more a flawless process. So the first example here is about commercial vineyards. It comes from Israel, so I was kind of like, what's up with these guys in the Holy Land always turning water into wine? It seems like something they like to do. But basically, this paper talks about using spectral indices calculated from planet data to measure the grapevine stem water potential, which can then obviously lead to much better cultivation practices. Usually this is done using like a UAV or electric probes, which is really time consuming and has limitations on how far you can cover. So this kind of greatly increased their sustainability and efficiency in their fields, in their test data. And they were saying that they could apply this to like a global model as well. The next example comes from river morphology. So what they did here was basically combined aerial imagery to measure these sandbars in rivers in Saskatchewan, Canada. This is from Robert Strick at the University of Brighton. And then they did the same thing in planet imagery and compared how much the positions change from those different images. And they were able to conclude that they could make reasonable estimates of the bedload sediment transport from just using the satellite imagery. So that really opens up the potential for global estimates of the bedload sediment flux for large and inaccessible rivers where you can't go in with like a boat or sonar, or you just don't have time to cover that. Or you just have like sparse rates there already. The next example is from Greece, Dimitris Poursanidis from the Foundation of Research and Technology in Hellas. This is basically a bathymetry study using pretty traditional methods of calculating water depth with multispectral imagery, but was applied with PlanetScope data. And what the authors found was that they were able to predict depth with a RMSE of about 3.2 at a depth of 10 meters, and at a slightly lower precision down to depths of 25 meters. And they concluded that the imagery was suitable for use in navigation because the results that they calculated were compliant with the International Hydrographic Organization requirements. So, they're offering a way to scale up temporally and also in availability this bathymetry mapping. So you can imagine applying this and getting really up to date to the daily or weekly all over the world. This is a really interesting study from Sarah Cooley of Brown University. So in the Arctic regions, a lot of freshwater lakes influence carbon dioxide and methane emissions. and as their shorelines change and become more variable, they have a greater flux of greenhouse gases. So, there's hundreds of thousands of lakes in these areas, and basically what these researchers did was use our planet imagery to monitor the shoreline change and then derive some of that flux on the greenhouse gas side. Just something that you probably would be completely unreasonable to do, over a time scale with aerial imagery or traditional methods. So again, just showing that expansion of possibilities using remote sensing data from space. This is a pretty interesting one. This is ship-based detection from Catherine Rice at the Naval Postgraduate School. Using a deep neural network, I believe they use the VGG 16 architecture for this. They're able to not only detect vessels with a really high accuracy, about a 0.83 recall and a precision of 0.85, but they're also able to classify types of ships and even fast ships by looking at the wakes. This has a lot of implications for, like illegal fishing or transshipments, security, commercial shipping numbers, as well as like dock management. And we also offer at Planet now, part of our analytics platform is port ship detection globally. So this is a project that I've been working on too, kind of on the other end at Planet, and it's been really exciting to be able to see that we can, with a really high consistency, be able to measure wherever ships are around the world at any time, especially when they're doing something illegal and they turn off their AIS beacons. This is one of my favorites, the Global Coral Atlas. This is a project funded by the late Paul Allen, co-founder of Microsoft, and also with the National Geographic Society. And basically, they've started mapping all of the world's corals with Planet imagery, and they plan on having all of the world's reefs mapped by 2020. So they've got an Atlas website already up, and just really important resource for our oceans, obviously. And it's just great to see that someone's actually endeavoring to really map the whole world's resource like this. And that's really the data sets that we're trying to kind of put together with our imagery. Well, the last two are sort of related. They use this same processes to get to their conclusions. Basically, leaf area index is not something that you can typically calculate from a RGB near IR satellite. You want to use the shortwave infrared bands, something that Landsat 8 has. The researchers Rasmus Holmberg and Matt McCabe were able to develop machine learning methods that basically took these took the Landsat 8 and calibrated it to the Planet data so that you could fill in all the gaps with the Planet temporal revisit rate and the higher resolution that we offer with the Dove imagery. And they created a model called the CubeSat Enabled Spatial Temporal Enhancement Model, or SESTEM. And they have these, and so you're able to do this sensor interoperability. This last one also now calculates evapotranspiration using that method, since we have the leaf area index from the last process. We're able to use that in the Priestley Taylor Jet Propulsion Laboratory retrieval model. And this work was done by Bruno Aragon in Saudi Arabia, where they're trying to grow crops essentially in the desert, and they're quickly depleting their groundwater sources. So just a really great study on being able to show that even with this CubeSat data that might lack some of the spectral characteristics generally needed, with this sensor fusion approach, you're able to still measure evapotranspiration and therefore more accurately monitor water losses in agricultural processes. A few additional highlights here. There's some seagrass change detection, suspended sediments in tropical rivers, shoreline change, and measuring river velocity. These are all coming from our academic program highlights, and you can read more about them on our website or ask me, and I can get you links to the different papers. And that kind of concludes the that part of it. I'm running really low on time. there's a, right, this is the last slide here. So given the theme of that data interoperability, there's been a lot of effort from players in the industry and led by Planet to work towards creating data products that can work really well with each other off the shelf so that individual scientists aren't responsible for cross-calibrating every single time someone does a project. So there's at the USGS in Menlo Park is the second analysis ready data workshop. And there's some links here that you can go to read about the last one. There's videos from that conference as well as a sign-up link, or just ask me later about it. But if you're into remote sensing and this isn't just for satellite imagery, but for any type of aerial imagery or LiDAR, et cetera, definitely check this out this summer. It's going to be a great conference. And with that, just going to leave. This is a quote that I really like, and I think really stands for what everybody in this room is doing and what we're aiming to do by having created this global time-lapse data set. So thank you, and yeah, let's make water happen.
So there actually is time for questions. So if you have questions, raise your hand. You got a mic running.
Questions? I had some resolution questions as far as actually looking at spatial versus temporal in greater depth, and kind of what the goals of Planet are on the spatial resolution. You know, right now it's pretty far pan out, like you're saying, it's not people on their cell phones, but I'm curious as an industry expert, what sort of timeline until we are grappling with that? I mean, that has exciting implications for water science and other sciences, but it also obviously has ethical implications.
Yeah, we don't have, we're not like developing a super zoomed in sensor or anything at this time. We're definitely always trying to improve the spectral characteristics. We have some really exciting tech demos kind of coming along in the future. But I think the focus for us isn't that we're not like really trying to look at that scale of things, and it becomes sort of unfeasible, or a lot more difficult at the rate that we're trying to do it temporally. I can show you a little bit a video of the way that our constellation works and the orbits work that lets us be able to do this, but there's not really a goal of trying to monitor individual people or see where they're at. But it is a really serious question, and I think it's one that we need to stay engaged with to answer, and that everybody should be thinking about. And if you look at facial detection in China, or how it's being used there to give you get like a ticket if you cross the road not on a crosswalk, that's a serious concern. Really, what we're trying to do is give that transparency to the world. So, if a country, for example, is acting malevolently, for example, there was the Rohingya refugee crisis last year was going on, and military forces were coming into villages and clearing people out. We're able to see that, right? They're also maybe able to go now see where people are at, or where their enemies' military installations are at, or a company might be able to see where their financial assets are concentrated for their competitors. But really, it's giving that transparency to the Earth for both sides. And so we don't do any like exclusive licensing on our imagery too. That's kind of one of the things where the way that we structure our plans. So we don't want to like just give that transparency to one side. Hopefully that answers your question a little bit.
A lot of satellite imagery stuff.
Mary.
Wait, sorry. Somebody was asking me a question in the back. So I'm curious, I see lots of opportunities for like these larger scale collaborations where you could look at things like global sediment production or regional freshwater storage opportunities. Are you guys involved with helping to coordinate different researchers to answer these larger scale questions at, those large spatial scales, or do you kind of leave it to every researcher to kind of independently pursue, or do you play any role in helping to kind of coordinate the different efforts that are going on?
We don't have like an official role coordinating any efforts, but that's part of why I'm here, and what I'm excited about personally is really getting this. A lot of people haven't ever heard of our data set, so trying to get the word out that this technology is available. We're happy to connect people as well through our academic program, and we have had like some events around the world bringing together some of our academic partners. We're also working to work with institutions to make that data available to the entire institution directly, and I think that will kind of increase the amount of people being able to collaborate on some of this data. The other thing I will mention is that there are concurrent efforts as well, in the interoperability space in just kind of defining the data and being able to catalog it, and making that available in a searchable, indexable way online. There's a project called the Spatial Temporal Asset Catalog, or STAC, and some people at Planet are also kind of behind that. It's an open source project, but we're heavily involved in defining that specification, and we think that having sort of these open source standards around this imagery and where it is, what's available, you're doing a lot more like reproducible research by providing access to that. Great, thank you.